So now we want to start exploring what's known as the integral, hence the name integral calculus. So the idea here is exactly what we saw in the last video, which is that the integral is equal to the area under the curve. So we had this expression right here. So the limit as n goes to infinity as I equals 1, from I equals 1 to n of f of xi star times delta x. And we had this as the definition of the area underneath the curve. Okay. So we have a different name for this, which is called the integral, which is also gives us the area under the curve. So it's basically just shorthand for this. But we also don't use this notation because this isn't always how we evaluate it. We don't have to look at the sums and take the limit every time to do that. And we can do it that way, and we will do it that way to start. But we have different formulas of finding this expression. So we don't write out this whole big thing every time. So we basically just have a shorthand notation for it. But let's just write the definition first for the definite integral. So if f of x is a function, and remember last time we said that it had to be a continuous non-negative function, so here we're dropping that. So is a function on AB let me move this down here. Let me spread this out, go to a little more room. The definite integral of f from A to B is given by this expression, but then we use the notation of this elongated s here. Okay, so you might have seen the symbol before. If you've looked at any calculus textbook, you've definitely seen it. So this is supposed to be an elongated s, which stands for sum because we're summing up the rectangles. And then we put the lower and upper limits, meaning the endpoints of the interval, on the top and bottom here as seen, of f of x dx is equal to this. Okay, so let's break down exactly what this notation is. And you might notice the Leibniz notation here, where the Leibniz notation for the derivative, the dx, is right here, right? So essentially what this is that this is the width of the rectangles, right? And this is the height. Okay, so in practice, this dx is mostly just telling us what the variable we're looking at is. Okay, so its physical meaning is the same as the delta x over here. And this will become important in various integration techniques that we look at. But in general, for simple integrals, this is really just telling us what our variable is. So just like we differentiate with respect to a variable, we integrate with respect to a variable. And this is what that variable is. So that's kind of like its functional purpose, even though its actual meaning is as the width. It's an infinitesimal width, but it's a width nonetheless. Okay, and it has the exact same meaning as in the derivative, where you had your dy over dx, and it was like this infinitesimal change in x, right? Exact same idea here. So this definition isn't quite over either. I just wanted to explain that first, but the full definition now. So the definite integral of f from a to b is given by this expression, provided the limit exists. Okay, that's not a given, of course, as we've always seen. The function f of x is said to be integrable on AB or is an integrable function. Okay. So we say that the function's integrable if this limit exists. So naturally, this means that a function does not need to be integrable. So we'll look at various cases where we know the integral it does exist and that the function is integrable. If we want to be really nitpicky about this, technically we would say that this means that it's Riemann integrable. So this is a specific type of integral known as the Riemann integral. There are different types of integrals. You really, like in statistics, you don't really get into that part too much. Like when you get into the theory of probability, like the very theoretical aspects of probability, you look at something called measure theory, and in that you're looking at what's called the Lebesgue integral. So that's the word Lebesgue. It's a name really, Lebesgue. But again, that's deep into the theory of probability. More like if you were to do like a PhD in biostatistics or something like that, you might run into that kind of thing. So we use the word integrable and Riemann integrable interchangeably, but just know that, it's not necessarily the only type of integrability. Something can be Lebesgue integrable, but not Riemann integrable. Okay, so we are looking at a specific type of integral. So anyway, that's just a bit of a tangent there. So let's look at some of the names of these different parts. Okay, so this part right here, f of x, this is known as the integrand. Okay. The x here, which is denoted in the dx, this is known as the variable of integration. Okay. And then the a and the b, these are known as the limits of integration. Okay. Okay. So not in the sense of like an actual limit, like a mathematical limit that we're doing, more in the like plain English sense of the word. Like those are the limits, those are the parts that we're looking at, right? So we didn't specify any conditions for the function, so let's look at some functions we know to be Riemann integrable. Okay, so we'll state this as a theorem that continuous functions are integrable. Okay, maybe not too surprising because continuous functions do tend to behave well, but we did see that continuous functions aren't necessarily differentiable, but this means that they are integrable. Okay, so let's go through an example with this. What if we wanted to take then x squared and do it from 0 to 3? Okay, x squared. So what if we wanted to evaluate this? We found a right endpoint and a left endpoint approximation for this. And I said that the actual area was 3. So how do we find that actual area? Well, just like with the derivative, we started with the definition of the derivative, taking the limits of the difference quotients So we kind of started doing it the long way. And then later we learned a lot of easier methods, such as the power rule and stuff like that. So we're going to kind of take the same approach here. So let's first do it with with the definition of the integral here. Okay. So first we want to take a partition on 0, 3. Okay. So the width here is going to be 3 minus 0 over n. Okay, so we want to keep n in the expression so that we can eventually take the limit of n as n goes to infinity, right? So we're going to look at this with widths of 3 over n. Now, if we look at the definition here, we need the widths and we need the heights, but remember, xi star can be any point in that interval. So it doesn't matter here if we do a right endpoint approximation, a left endpoint approximation, any of that on this part. So we could use the right hand one or whatever. All right, so on 0, 3, we know this to be an increasing function. So if we use the right endpoint ones, it's like an upper sum, right? So if we consider the subinterval xi minus 1 to xi, okay, we want to use xi because we're going to do the right endpoint. You could do the left one too. It doesn't really matter. We're just picking one, essentially. So one helpful formula with this that we'll kind of write, I can just write it up in this little crevice right here, is that a general formula for the ith, the xith point is x0, which is a, plus I times delta x. Okay, so here x0 is equal to a. So generally we say x0 equals a and xn equals b. Okay, so this right here is a general formula for the xith point, which will help us here because we're doing the right endpoint approximation. Okay, so if we do that for our case, x0 is equals a, which is 0. So xi equals 0 plus I times delta x, which is this, right, the width. So it's equal to 3i over n. Okay. So we want to look at the sum, which includes f of x sub I. So this is going to be f of 3i over n, which is 3i over n squared, which is going to be 9i squared over n squared. Okay. So we're starting to get the parts that we need here, right? Just looking back at this definition, we need the f of xi, the delta x's, and that's really it. Okay. So we have our delta x, which is 3 over n. We have our f of xi. So now we can start to put this together. So this is going to be the sum from I equals 1 to n of 9i squared over n squared times 3 over n. Okay, and if we go ahead and just write that out. So we're just looking at the summation part first, just to kind of simplify it. Then we'll take the limit. So this is going to be 27i squared over n to the third. Okay. Now, the actual index variable is I, so everything that's not an I we can take out of this. Okay, so we could rewrite it like this. So on the inside, we just have I squared left. Okay. So there's one more formula that will be helpful here. And I'm just kind of adding these in as we go because like I've kind of suggested, we're not really going to do these by hand like this. We're more going to use the easier techniques to do these. So specifically, when you take the sum of I squared like this for the first n terms, the general formula for it is as follows. N times n plus 1 times 2n plus 1 over 6. Okay, so this is the general formula for the sum of I squared over the first n terms. Okay, so if we multiply that out, we're going to get 2n cubed plus 3n squared plus n over 6. Okay. Now we can simplify this further. So we're just simplifying as much as we can before we go ahead and take the limit. So let's see, we'll get 54n cubed plus 81, right? Yeah, 81n squared plus 27n over 6n cubed. Okay. And then just go ahead and break this up. 54 divided by 6. So we get 9, and then n cubes cancel out, so that's just 9. So you can already see where the area is probably going to pop up here. 81 divided by 6. You can take a 3 out of both of those, so we have 27 over 2n. You don't have to simplify it because they're just going to go away anyway, but never hurts. Okay, so I think that this is what we'll end up with. Okay, so this is the expression for the summation. So this is like the general expression for the right endpoint approximation of this for a general n. Okay, so like you should be able to go and plug in 3 or 6, for example, and get the answers that we got in those last few videos. So now the definite integral from 0 to 3 of x squared dx is then going to be equal to the limit as n goes to infinity of 9 plus 27 over 2n plus 9 over 2n squared. Okay, these two terms are going to 0, so this is just going to be 9. Okay, so that's how we would get the general area under a curve the long way. Evaluate the definite integral the long way here. So like I said, we're not really going to do it by hand like this. I just kind of wanted to show one example of exactly where this comes from. So we're going to explore something called the antiderivative, and that'll allow us to evaluate the integral a lot more easily.